what's going on.
Nice. I'm glad. Whatever, this is not really gonna work. I need like more of an angle.
Right up by the door.
And he said like they have a recording of it, but like only the people here know that, like the other people don't know that. So
Also, I'm missing like half the notes for this, so that's why I'm here.
true.
Because like I missed every Thursday, and apparently we actually did stuff, and I was not so.
If you guys want, swipe in right as you're walking in. The swipe right up there. That way I can send out all my notes, all the tests, and the video of this one for last semester. Send me a message, and I'll go ahead to the list. Oh yeah, that's true. It'll say processing and then successful.
It's been good in the past.
Swiping, like switching on your
Is
phone.
my stream not working? Here we go. Here we go.
More people at this one than the last one. This is bad because Kitty 228 is only available so many times. That's the only way to go, place to go. Might have to start doing those Sunday evening reviews.
Why 7 instead of 9?
Because it's a Monday, and Mondays I have a chapter meeting at 9. Plus, I have to be up at 5:30, so the 9 o'clock reviews are a little difficult. I work at work at 7. It's about a 40-minute drive.
Where am I going to put my like,
Not
class
far.
notebook?
No, it's just my car.
You can put it on the computer.
Yeah.
You can put it on there.
Next semester, though,
You're going to
taking classes.
No, you can put
I'm starting at 9 a.m. on Monday, Wednesday, Friday, 10 a.m. on
Girl.
Tuesday, Thursday. On Monday and Tuesday, I'm done by 1 o'clock.
Okay.
Solid.
There's extra support.
Gibadon,
Okay.
terrible, terrible company. You never go there. It's miserable. They have no idea what they're doing. Yeah, if you could just swipe in,
Yeah.
and I'll send you all the notes and everything after.
Thank you so
Right
much.
now, I'm designing signs.
Oh, that was my
Like
last
signs to hang in the building.
I was like,
manufacturing
oops.
plant. I'm sitting on Visio
Oh, it was just
for
a
8
laptop.
hours
It wasn't
every day,
anything expensive.
designing
No, I think
signs.
that's my photo.
That's been
It's
my
fine.
full-time job for the past 2 weeks.
Oh, that's no. Put it in like the bottom one or
Not
something.
fun.
Yeah, that's taking up all the.
Miserable.
Girl.
I don't
They
understand. I
said, oh yeah, just make like these
like, I
5 or
don't.
something. And I did those.
Literally.
Well,
That's
like,
the
oh,
wrong
well, we can
person.
give you 100 more.
Okay,
I'm like,
just put it in the bottom. That's so funny.
I just take
it's
it
supposed to
out.
be like implementing a system called 5S, which is
know what I
like
did.
helps manufacturing processes move faster. But like
I'll probably just be on my
labeling and
computer.
organizing things is a part of that, and the organizing and labeling part that I got is the design science. Especially because then I design the signs, I send them to somebody to make them, and they change up the format. Yeah.
We all have the same dad.
Yeah.
Mine feels like it's
Thank
such
you.
a
It was getting too long. I was like, I have to take.
Yeah.
Let's put it all.
It's
The way I do this.
like, look, whoa.
Also, I have some computer programming like recitation here. None of these can fit a laptop on them.
Yeah,
That's why I need to have two.
Yeah, I think like every desk is filled.
Do you want to move?
Yeah.
Okay,
Also, there's like chairs.
that's true.
If you're coming this late, you deserve to.
That's so mean.
You yelled at me. You're like, should I come early for seats?
I didn't tell you that. I said that's why you gotta come early. So like for me, so I can get the seat.
Oh, okay. Whatever you say.
Yeah.
I know it's still water at some point. Now it's all like warped.
Yeah. Okay. I'm testing the audio. This should be okay.
How long is this one take?
2 hours. Yeah.
What are we doing?
Everything.
I normally give people 5 minutes, just like 7:05 I'll start, and then you know what?
We're already pretty full.
Just still, I had a Diffie Q review in here for the first test of the year. That door was propped open. We had like 4 people sitting out in that stairwell. It was very crowded for that.
We've what at this lab?
They have like a big queue thing. They have to have people sit in the
Yeah.
stairwell.
Oh my god.
So there's no room.
That's crazy. That's so nice. It saves lives. I should post it in the group chat.
Does anyone watch that? Remember him saying probably not.
Last time a lot of people did. But this is only my second one, so.
Wait, your second one for math? 'Cause I know you've done calculus.
No, this is my second live stream. Yeah.
Oh, you just recorded it. You didn't
Yeah.
watch it.
But then recording it like
Technically,
stopped.
it is a local
So live streaming,
problem,
the only reason I'm live streaming
but
is
it's not.
because
It's more
one,
of
it
a
gets it
change.
to the people
Okay.
faster,
It's like I'll do the
and two,
problem,
I don't have to store it all on
Yeah,
my
that's
phone.
what I
But
was
it's
saying,
not-
save it. Delete the memories.
it's not as much. Yeah, it's more of a chain rule problem.
Okay.
Although it technically is finding the maximum of something. Okay, 7:05. If anybody's later than this, they deserve to miss stuff. So that's how it is. So if you guys didn't swipe in as you're walking in, I'll leave that there so you can swipe out as you're walking out. I'll send out after this my notes, my test, and then last semester when I did this review, I had SIT TV record me, so I'll send out that video as well. I'm not allowed to post it on Facebook because there's like copyright stuff with like intellectual property of the tests, and since I'm using test questions, I can't post it on Facebook. It's a whole big shindig, but I can send out the link. So if you want to send the link to your friends, you can do that. I just can't post it on Facebook. But anyway, if you don't know me, my name is Jake Shozer. This is my email. If you have a question between the end of today that you don't ask and when you have the test on Thursday, send me an email. I'll do my best to answer it. I'll probably do it at work because I don't like designing signs. So that's what they have me doing right now. I'm a mechanical engineer. They turn me into a graphic designer. So I'll just answer some emails, teach some MA124 while I'm at work. But hopefully they do what they did for your midterm for MA123 in that they keep to the structure of past semesters. Because if they do that, your first question is going to be that one, your second question is going to be on that, third question will be that, fourth question will be that, fifth question will be that. If they do what they did on the final and change shit up on us, then it's going to get a little more interesting. Then you actually have to think. But on the bright side, everyone will be facing a challenge together. So with the curve and stuff, you'll all be good anyway. From what I heard last time, everyone got one question wrong. So like, there's no way they can just have the top score be an 80, or like the average score be a 40. So like, there's always some curve. Even if they say there's not a curve, there's always some curve. So with that, are there any specific topics that like people are struggling the most on before I even get started, so I know what I can emphasize? Or are we good with everything, or are we just like, I have no clue anything that's going on?
That last one.
Okay. Don't worry, we got this. So, I'm going to start off right with this first one, using a table to estimate. It's not even a difficult concept. It's not even really, it's just, I'm just going to go right into the problem because there's no teaching or learning behind it. It's just when you see this table, know how to use it to take a derivative. So this was the first question on my test. This was the first question on the test last semester. Hopefully it'll be the first question on the test this semester. It's a nice, easy one to get started with. Up here, so 1.8. This is 2. 2.1. So what the exact problem said was use the table of values of f of xy, which is this, to estimate the values of df dx at the point 2,3 and df dy at the point 2,3. So when we're estimating derivatives, what does a derivative just mean? It's the change in the function over change in x at this point. So we need some change in a function over change in x, which means we want our function final minus function initial over x final minus x initial. Right? Going back to pre-calc definition of derivatives. So we know that we want it at the point 2,3. So we know that one of our points that we're using has to be the point 2,3. So at x equals 2, y equals 3, I have 7.3 is my f of xy. So this is my f value. All of these is here. So final minus initial, when we anytime we do our delta. So we have our final, which is going to be that 7.3, minus initial, or final function minus initial function, final x minus initial x. So the x that correlates with the 7.3 is going to be 2. Now, we're going to move to either this box or that box. We need to decide which one. Since it's asking for a change in x, we're going to say, okay, well right now I have an x of 2. I need to move somewhere where there's an x of something different than that so I can have a change in x. So right here, this box right here has a different x. And it's fairly close to 2, so I know it's a good approximation. So I'm going to say that my final x, or my initial x, so final minus initial, is going to be 1.8. And my initial value of the function is going to be that 7.1. Because I want to change in x, I want to know how the function changes as x changes. I don't want y to play any factor, so we're keeping y exactly the same, because it's 3 for both of these, but we're changing x, I want to know how the function changes. So that's how we got these numbers. Now you just do math. You have 0.2 over 0.2, which is equal to 1. That is 3 points out of 40, so that's almost 10% of your test right there. Does that seem pretty doable?
Yeah.
Not too intimidating? So now, for this one, basically the same thing. We want delta f over delta y. We know that we're still starting at this point 2,3, so we still need 7.3 minus something. And we know that our initial y value, or our final y value, is 3. So now what goes in these two? What's going to be our initial function, our initial value of the function? 6.3. This one right here. Because we want to keep x the same, but we want to change y. So we have 6.3. And then what goes right here? 2.5. And now 7.3 minus 6.3 is 1. 3 minus 2.5 is 0.5. 1 over 1/2 is 2. Does that not make sense to anybody? Because this isn't even that much it's not even really calculus. It's just being able to read the table and understand what it's asking. If that makes sense, then we'll move on from that. Like I said, if they follow the structure of past years, that's your first question. And that's also worth 6 out of 40 points on your test. So if you can get that, you're off to a great start. They put the easy one up front so you can be confident before you get your hopes crushed by the next one. So that's our first question. Done. Now we're going to move on to finding tangent planes. So now this is really getting into some more of the actual calculus that's going on here. So we're going to talk about some linear approximation. And finding a tangent plane. So I'm actually going to do this part first and then go into that. So when we want to find a tangent plane, the whole idea behind this is, I've been taking multi in a while and see how good my art skills are still. So here we have a 3D plane. We got our X, our Y, and our Z. So we got some 3D space. And we have so if you can see kind of what's going on there, we have like a parabola, kind of bowl type shape upside down. Does that make sense? So it's basically the way that the old multi-teacher who retired this past summer, Mr. Maz, loved him, he would call this the salad bowl. It's the salad bowl, but it's upside down right now, if you guys can imagine what's going on. And what it's asking us to find a tangent plane. If you're thinking about a tangent line, it's something that touches another line only at one point. So if we're finding a tangent plane, it touches a surface only at one point. So this is where it's going to get more difficult to see. But if we have some plane here that is kind of in front of this whole parabola, 3D shape, but like kind of like right there, you see like one touch of that parabola, kind of just touches it. It's probably difficult to visualize it, but if you can imagine what's going on is you have a bowl and we're just resting a piece of paper, just touching it at one point. That's what this situation is. So we're trying to figure out what's the equation for this plane that touches this paraboloid, is what it's called, at a specific point that the question's going to give us. So that's the whole idea behind finding a tangent plane. So now, getting a little bit more specific to the types of problems that you're going to see. First, I'm going to say that some point A, B, C just represents any point or a point on the plane. So in this picture right here, this point right here is A, B, C. And the reason why I'm doing that is because it's going to be plugged into a generic formula that I will now write down. So we have, in order to find, this is the general form for your tangent plane. It's going to work like this every time. you have f of x evaluated at point A, B, C times x minus a plus f of y evaluated at point A, B, C times y minus p plus f of z of A, B, C times z minus c is equal to 0. And basically what you want to do is, once you know what this point ABC is, which it I think has to tell you, because I don't think you guys know any way of finding a point that corresponds, but they're going to tell you what that point ABC is. So all you have to do is find your partials. Which is your fx, your fy, and your fz, and then plug everything in. Now, if I'm remembering correctly, they might have taught you a different way where there's like a z on one side, I think. This is the same thing, just reformatted. So you're basically, because I think they used to have the z by itself on one side and then like a constant on the other side. That's not really needed for solving questions of a tangent plane. This format works, and in my mind, it's the easiest. Because I remember when I was taking the class and I was like, why the hell are there two different ways to do the same thing? And then I realized it's the same thing, and then to me, this was the easier way to do it because it's more consistent and it'll work every time. But you're going to be given some function, this fx, fy, fz. That function is this paraboloid down here. So some surface that you have, some 3D shape. And then it says we want a plane that touches that shape at this point ABC, is the way that the question is going to be framed. So you take your three partial derivatives, you plug in your point, and then you have your equation of that plane. So now, does that, the general sense, make sense to anybody? Okay, because now we're going to jump into the problem. So if you weren't somebody that just shook your head, then hopefully after I do the problem, it'll make more sense to you. If it doesn't, let me know, and I'll explain it in a different way. Okay, so this problem worth 8 points, so this is 20% of the test, says find an equation of the tangent plane. So find the equation of tangent plane to the surface xy plus yz plus xz squared is equal to 3. And then it says at the point 1, 1, 1. So this is what we're dealing with right now. Now, it's not going to matter in this case because it's just a constant, but a good practice before you start taking your partials, take this, move it over to the other side so that way you have it equal to 0. In this problem, like I said, it's not going to matter because when you take your partial derivatives, this is going to just go to 0 every time because the derivative of a constant is 0. But it's good practice because if it wasn't just a constant, things might get a little tricky. So I'm going to say move this to the other side. So I'm just going to say minus 3 equals 0. And now that's the equation of the plane that we're working with. So just like I said, find our partial derivatives, plug everything in. So let's start out with our f of x. So who is unsure of how to take a partial derivative? Raise your hand if you're unsure. Plenty of people have no clue what they're doing. It's fine. But the whole idea is when you're taking a partial derivative, we're saying that x is being treated as a variable. All the other variables we're treating as constants since we're taking f of x. So looking at that, x is my variable, y is a constant, so the derivative of a constant times x is just that constant. So my f sub x is going to be y. This is just two constants, so the derivative of the constant is 0. So I'm going to leave that out. And then the derivative of some constant times x to the first is just, again, that constant. So it's y plus z squared. And then the derivative of -3 is just 0. So my f of x is that. Now I'm going to continue with my f of y, which from the first term is going to give me an x. Second term is going to give me a z. And the third term is going to just drop out. Then my f of z is, I'm going to get 0 from that. I'm going to go to y from that. And here I'm going to get a 2xz. So I have 0, I have y plus 2xz. Because again, we're taking the derivative of the z squared, which would be 2z, and we keep that constant out in front. So we have 2xz. Now, we plug everything in. Because this is evaluated at the point a, b, c, which in our case is 1, 1, 1. So for x we plug in 1, for y we plug in 1, for z we plug in 1. So 1 plus 1 squared is 2. 1 plus 1 is 2. 1 plus 2 times 1 times 1 is 3. Well, now I have my f of x, I have my f of y, I have my f of z. I know what a is, I know what b is, I know what c is. So I'm just going to plug it in. So my f of x is going to be 2 times x minus 1 plus f of y is again 2 times y minus 1 plus f of z is 3 times z minus 1 is equal to 0. That is the equation of this plane that touches that surface at the point 1, 1, 1. Question?
So what if we give you an equation that doesn't have a z in it?
So it's just x's and y's?
Yeah, but the point is still 1, 1, 1.
Then it's constant in the z plane. So then if it doesn't have a z, then your f of z would just be 0. Do everything the same exact way, but your f of z would go out to 0, so this last term would drop out. Makes sense? Any other questions on this? Because, like I said, this, 20% of your test. There's 8 points right here. Do you think you can handle this? Because the first question was, we think, pretty good. Second question, well, this was actually question 4. The second one that we're doing, pretty good. That's 14 out of 40 points right there. Yeah.
14? I take a 14.
Approximate another point.
40.
No. Not today. That's less than a 50.
That's that one right
Yeah,
there.
a lot
We
less
didn't
than
have it on our test, but I'm pretty sure I have a problem in here.
It's literally a 35.
Yeah, I have a problem in here.
35%.
So, does finding a tangent plane make sense? Because if so, then I'll move on to the tangent plane approximation, otherwise known as linear approximation. Boom.
What if I break out a salad right now?
Do what you want. I went to Froyo because Froyo this month is buy one get one before 6 p.m. So you do is you fill up half the cup and fill up the other half, so you get yourself. Yeah. So I did that, and that was my dinner, I guess, and now I just feel disgusting. I didn't actually have dinner today. Like I had Froyo. I'm just like, oh.
Rip, do you want some veggies?
I want your chips.
I ate them already.
So,
Top 10 anime betrayals.
the point that I'm going to argue when I'm teaching this next section, when we're dealing with linear approximation or tangent plane approximation, is that you already know how to do tangent plane approximation, you just don't know it yet. Because whether it was back in middle school when you were first learning like graphing and all that crap, integrated algebra, or if it was in high school, whenever it was that you learned like the graphing stuff and how to like linear approximation with 2 dimensions, if you're given an x value that's close to another x value, you're like changing y, like changing x, find the slope, all that good stuff. It's the same exact thing, except now you have a 3rd dimension that you're doing it with. It's the same process. The formula is actually the same exact thing. You just have to add on a 3rd dimension. I'm going to show you that right now. So if we were dealing with 2D and they give us a line, so we have a graph right here. They give us some weird fancy line. We don't know what the formula for it is. And they give us a point right here that it tells us that the coordinate is 3, 2. And it asks you to approximate the function at 3.02. Well, if you knew that you need to find the y value somewhere very close to right here, and you had this function, you would take the derivative at that point, 3.2. You would multiply it, because your derivative is your df over, or you're changing y over changing x, because we're in 2 dimensions. So it's your dy over dx. So if we find this derivative, say we find the derivative to be, so we find the derivative to be 2. Because we're given this formula, we plug in the point 3.2, we take the derivative, we find that the slope at that point 3.2 is 2. Well, I know that that's going to be equal to my change in y over change in x. Well, my change in x is 3.02 minus 3, so it's 0.02. You know your initial y value is 2. You have 2 minus y2. And there you go, you have a way to find your y value, right? That's something that we should all know how to do, hopefully, by this point.
We just did the
That's
trade-off ones.
dealing with everything in 2D. Now we're dealing with 3D. It's the same exact thing, we just have another dimension. So if you were to try and figure out that approximation with 2D, you would say, I have some f of x that I want to find. I would plug in f of a plus f prime of a times x minus a, which is basically what we did right there, just a little bit shifted around. So our f of a is our initial value at this point right here. So this is our point A. So we had our initial value, which was 2, plus our derivative, which we said also is 2, times our x value, which we know is 3.02, minus 3. And then we could find the approximate value of this point. We'll call it b. Moving into the third dimension, we don't just have f of x, we have f of x y, because now we have two variables that we can change in order to approximate a z value. And what it's going to look like is some function of a, b. So this is your initial condition. And again, we just have one more term here because we have one more dimension. Plus, same way that we have a derivative times our change in x, we're going to have our derivative evaluated at our point AB times x minus a. So it's our derivative with respect to x times x minus a, but we have another dimension. So we're going to go derivative with respect to y times x minus a. Or times y minus b, sorry. Because this is our y, so we have our y and our y. And this is your formula for tangent plane approximation. Do you see the parallel between the 2D and the 3D? It's the same thing, we just have to account for the extra dimension. And once you understand that, it makes it a whole lot easier, because you don't have to memorize it, you can just understand it and think when you're at the test, rather than, I need to memorize this formula, I need to memorize this formula. Because hopefully that one you have memorized already. So, I'm not going to draw a picture for this one, but say we have some point where A is 1 and B is 2. And you know what, we'll actually use this right here. We have some point 1, 2, 3. So my A is 1, my B is 2, my F of AB, which is my Z value, is 3. I want to approximate 1.03, comma 2.04. If I were to have the equation, this one I just made up on my own, so I don't have an actual formula for it, but I would have some equation for the surface like I did in the last problem. I would take the derivative with respect to x, and then plug in 1 and 2. I take the derivative with respect to y, plug in 1 and 2, plug everything in. I have all numbers on that side, and I would get an approximate value for this f of 1.03, comma 2.04. Does that make sense? Who is still confused? Yes.
Just say that one more time. So you're using those as A and B?
So what A and B are is your initial point. So our initial point is this 1, comma 2, comma 3.
Okay.
And this 3 is our initial value. It's our Z value at our initial A and B, which is our 1, 2, 3. So if I want to find an approximate value of 1.03, comma 2.04, those are my x and my y values, because that's a new point that I'm trying to find the value of the function at. So this f of 1.03, 2.04 is going to be equal to f of AB, which is my z value, plus whatever my f of x ends up being, evaluated at the point 1, 2, times x, which is this 1.03, minus 1, because 1 is my a value. And then I'm going to go plus f of y, evaluated at 1, 2, times y minus b. And if you had some function to describe the surface, you would find your f of x, your f of y, and that would be your answer. Does that make sense? Are there anybody else that's unsure of this? Yeah.
So
kind of just ignore the z value?
So you're saying this z value right here, this 3 is your f of ab. Because it's your function of your x and your y, or your a and your b. That's where it comes into play. Any other questions? If there's no other questions, then I'm moving on to some contour diagrams. Because we didn't have a specific question on our test asking us to do tangent plane approximation. Like I said, these are our 5 questions. So if we're all good with that, I'll move on to some contour diagrams.
Once you got that, and are you done, or do you have to do something?
So, if you were to find your f of x and your f of y values, you would get numbers as a result.
So you just
You'd evaluate all of this, and you would get some z value that would represent the z value at this point right here. This point being 1.02, 2.04, comma z. That z value is what you would get out of this. Everyone good with this? Sweet.
I forgot we even did contour diagrams. That felt like 123. Contour curves, you know, when you're like, oh, it's z equals 1, it looks like a circle, and you draw it. Like z equals 2, oh wow, now it's that. You know,
Oh. You mean like those are the points of x and y where it. So
Okay,
it's
contour diagram.
it's when you draw it in a
Who has
2D.
taken earth science in like middle school or high school?
I actually did it.
Okay, about half the room. I'm assuming most of those people are from New York.
Yeah,
So
in
if,
school.
if you've taken earth science, or if you haven't, if you've ever looked at a map, or if you've looked at a news broadcast where they have all those lines saying where it's the same temperature, like, oh, all along this line it's 71 degrees outside. Or if you look at a map saying all along this line it's an elevation of 1,500 feet. Those are all contour diagrams. And what they're saying is everything along that line is the same based on submeasurement. Well, with a contour diagram that we're dealing with in this class, we're just saying everything along that line is the same z value. It's the same, when you plug in x and y, you get the same result. So, contour diagrams. It's a way of representing a 3D object in 2D space. Because if you're going out hiking, you can't really bring a 3D model of the mountain with you. You have a 2D map, and it just has lines on it to show you what the elevation is everywhere you go. Or if you've ever seen like some of those maps that have like the geographic maps where some areas are red, some areas are blue, those are all showing the different height elevations, which is essentially what this is about. So a way that you can think about it is it's a bird's eye view. You're looking straight down, and the closer that the lines are means a steeper elevation change. So I'm going to draw this picture again to give you a little idea of what kind of thing you might see. So this one is the real salad bowl. It's facing up so we don't spill our salad. It's so sad. You guys are never going to get to have Maz because he retired. Everyone knows this as the salad bowl. He had a very Eastern European accent. You also had your truncated soda can, which is like a cylinder cut off by a plane. You have your ice cream cone, which is like a cone, and then a sphere on top. And you're just never going to get to know any of those. You'll be learning from a different professor. It's so exciting. Anyway, this is the salad bowl. And as you can see, this touches at the very center, so the z value, the height at the origin is 0. And as it goes out in all directions, because it's a bowl, the height, the elevation goes up as it expands out. So if I were to draw a contour diagram of this, I want to represent this as a 2D shape. So I'm going to draw a 2D where that's my x and that's my y. So I'm now looking down, straight down at this from the top. So at the very center, my value would be 0. So I'd have 1 point of just 0 at the middle. And if I move out a little bit to some point where the elevation is all 1, I would have a circle. And you can label that as 1, because everywhere along that circle, the elevation is 1. And you can think of that as this being this circle right here. But then if I move out a little bit more, my elevation is going to be 2. Then I move out a little bit more, my elevation is going to be 3. I move out a little bit more, and my elevation is 4. I move out a little bit more.
No way. Oh
my elevation is 5. So if I did a good job of drawing this, you'll notice that as I get further out, the lines are getting progressively closer and closer together. And the reason why that happens is because as I move further away and I get higher up, I'm now raising my elevation at a faster rate. So I don't have to move as far out from the origin to get a bigger change in height. Does this representation, can you visualize in your mind how this is the 2D model of that looking down? Because again, you don't need to be able to visualize it, but it helps very much for understanding the problem. So if that makes sense, I'm going to move into the problem that we had on our test, which was, it looked a little confusing, but it wasn't that confusing. It was just annoying because they threw an ln in there. Nobody likes ln's.
True.
So what the question read exactly was, let f of x, f of xy be equal to the ln of x squared plus y squared.
Super basic calculation.
Derivative of arctan.
Grab that chair if you need this, if somebody needs this chair. Do you want a chair? We have an extra chair over here if you don't want to send them. Or if you're comfortable on the ground, go for it. Okay.
No, you're good.
Merry Christmas. So, this was the third question on the test, right here.
Okay.
The third question on the test gave us that. You see the ln of a circle. This is like, what the hell's going on right now? So you got squares, but they're adding, so you can't even take the square root. But then you have the ln, so you're like, what? And then it says, part A was draw the level curves. So draw level curves for c equals 0 and c is equal to the ln of 4, both on the same set of coordinate axes. Now, all it means by level curves is one of these lines is a level curve, because all along, if you were to walk along that line, it would be a level path if they're all at the same elevation. So draw the level curves for c equals 0 and c equals ln of 4. So who knows what to do? Yeah.
You just say your function equals 0 and ln equals 4.
Okay, so we have ln of x squared plus y squared is equal to ln of 4. Okay? We have to draw that. Now, you're actually onto something that's a whole lot better than the way that I did it. But you have no clue what that way is, so that's kind of toughness. Does anybody else see what he's got? Yeah. Yeah. So what she said was, if you raise each side to the e, your ln's go away.
I thought that was just assumed, Jake.
I didn't say it. So we have x squared plus y squared is equal to 4. Now, it started off looking really weird, but what is that?
It's just a circle.
Circle.
Hell yeah.
We got a circle going on here. But now that's not a very good drawing. I gotta like put some labels on it. I gotta like, we know that we have like an x over here and a y over here, but like, what's the radius of the circle? So I can put like, this point right here is 2, this point right here is 2, you got a negative 2, and you got a negative 2. So there's your level curve where c is equal to ln of 4. So let me backtrack a little bit. When it's saying a level curve where c is equal to 4, it just means that this c is your constant. So the constant elevation that you're at. So it's basically saying that this function, we want to draw the curve where this function is equal to 0, where this function is equal to 4. Which is why we took this and we set it equal, I did 4 first because that one's more clear to see. But we set it equal to 4, or sorry, ln of 4. And that's how we got down here. And then the ln's go away, we're left with that, and we draw that circle. Does everyone see how we got there? Now we need to draw the curve for 0 as well. So what we're going to do is we're going to do the ln of x squared plus y squared is equal to 0. So now you can't just do both sides to the e.
Why not?
Or you
Yeah.
kind of can. What?
Shit.
You can. That makes it easy again. So you have x squared plus y squared is equal to 1. And if you're really smart, you know that that's a circle with radius 1.
You're the one
And
taking
that
like 2
is
desks.
5 points on your test.
Okay.
So this is actually easier than the way that I did it. Yes. What I did, which is, this one it works out nicely because they give you the ln of 4 and it crosses off well, but there's times where it might be a more difficult formula where you can't do it nicely like that. So if you can do it nicely like that, go for it because this is going to save time. The when in doubt way is you go back to your old friendly childhood game, connect the dots. So you draw a coordinate axis, so you got your x and your y. And you're going to start making some dots. So I'm going to go 1, 2, 3. Try and space them out as best as you can. Probably start with like 2 units on either side. And then you fill in all the rest. So I'm going to go a little bit quicker now. The better you space them out, the better the picture will look when you connect them.
Oh my god, this is true. This looks like slope field. Did you do? I got every single
And then you
question.
start plugging in.
I'm just an idiot.
So ln will start right at the origin.
I can't do this. I can't do
Start right at the origin. If we plug in 0 squared plus 0 squared, the ln of 0 is nothing. So we have undefined. Right here we plug in ln of 1 squared plus 0 squared. It's going to be the ln of 1, which is 0. And it's going to work out the same way for all 4 of these points because it's going to be 1 squared plus 0 squared. So these are all going to be 0. These 4 corner points are all going to be 1 squared plus 1 squared, which is going to be ln of 2. And then you move out here, we're going to have the ln of 2 squared plus 0. So this is going to be ln of 4. And then it works out that this is also ln of 4, ln of 4, ln of 4. And if you want, you can keep going, start filling in some more. It works out that this is ln of 5, so is this one. So is that one, 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 so is that one. As you can see, the circles are starting to form. And then this is ln of 8, ln of 8, ln of 8, ln of 8. Again, it's just literally plugging in the x and the y value into that formula that they give you. And then you connect the dots. So we want to draw the level curve for 0. I see all my zeros. I see that it's kind of formula circular shape because I don't want to just draw straight lines here. But draw the best circle that I can. And there's my level curve for c equals 0. And this is my level curve for c equals 4.
Okay.
C equals ln of 4. This is the when in doubt. You have no idea, like you said, ln of x squared plus y squared equal to ln of 4. You have no idea what to do. You can't think of how to simplify it in your head. You don't know how to draw x squared plus y squared equals 4. Put down some dots, evaluate them, start connecting some dots. Yeah.
Is level curve always going to be a circle?
No. On anything they give you to draw, it probably will be. Because if they give you some funky shape where you have to draw a level curve that's like that, it's not going to be clear enough. You're not going to be able to know clearly that that's the shape that it's supposed to follow. You would have to plot probably 4 or 5 points in each direction, which would just get absurd.
Okay.
So I can't guarantee it's going to be a circle every time. It might be an oval, but I don't think they'll go anything beyond circle or oval for having to plot a level curve. Yep.
Or square, I guess I should say.
Because the whole level curve stuff makes sense.
Like they could do a squared
How to
subset,
draw it.
like absolute
Yeah.
value pyramid thing.
Are those two the same?
Yeah.
Then how
These
come
two,
it's 1, how come it's 1 and then 2, and then for that it's 0 and L?
so these values that I have labeled right here, those are the z values at those points. So if I were to take these, like, now think of this as the level curve. Think of it as a 3D shape. If I were to now look at this from side angle, that point right there, the z value, the elevation, would be ln of 4. The value right here would be 0. It would be flat on the plane. This right here is the x value of that circle, the x value of that circle. Just that way we can specify the radius. So if you were to draw it like this, you should probably specify here, like c equals 0, c equals ln of 4. Just that way they know that you know which one is which. If you were to draw it this way, you should specify between the two. But yeah, these are the x and y values, whereas this is the z values for the actual level curves. Yeah.
Circle rather than like a triangle.
It's not going to be straight lines. Yeah. Because then think about that. Think about what the actual 3D shape would look like. You would have like straight lines. It would be like a. What looks like that? It would be like
Absolute value.
Absolute value?
yeah, pyramid. Yeah, it would be a pyramid shape, and they're not going to have
You're a genius.
that. A four-sided pyramid.
I was like joking.
Well, like a four-sided pyramid cut off at the bottom.
I
so you have zero
bet
down
they're
the
doing
top.
absolute value. So
It's-
put down the
if you're drawing one, it's going to be some sort of
Oh, they do.
curve.
The written homework was absolute value. This is bullshit.
And then also, when you're drawing them, make sure you don't
Did you have to
cross
do it?
over another line. So like I know this right here is ln of 5, which is greater than ln of 4. So I can't go outside of 5 and then back inside, because now I'm saying that everything inside this curve is less than 4, which makes sense. ln of 2, 0. I can't have a 5 up there because that just doesn't make sense. So that's another thing to keep in mind when you're drawing the level curves. If you're a little bit more
My
unsure
calculator.
of what the shape is going to be.
Oh, what does it mean that it's undefined at this end? What does that look like? It's just-
It wouldn't exist. So like the shape would cut off at some point. So like it wouldn't touch the origin. Cool. Now we're going to go into part B of this question. Because you don't have part A if there's no part B. Part B says estimate f of 0.9, comma, negative 0.2 using linear approximation at 1, 0.
Command V.
So now we get to put some linear approximation
When do I do
into
that?
test, into use.
When do I do that?
When he switches to the next topic.
Okay, I'll try to remember. I got it.
So, for linear approximation, also known as tangent plane approximation, who remembers our formula? We start off with f of xy is equal to, what is it? F of AB plus
Fx
f of x evaluated at AB
x minus a
times x minus a plus
x
f sub y evaluated at AB y minus b. So that was our formula to find the approximation. So the whole point of this problem, it's a little bit easier to visualize what's going on with our approximation. So we're saying that we know the value at 1, 0. We know the value of the function is 0. It's at 0 elevation. But we don't want to know the height at the value 1, 0. We want to know the height at value 0.9, negative 2, negative 0.2. So we want to know, like, right. We want to know the z value at that blue dot right there. So what we're going to do is we're going to find a plane that's tangent. We don't even really need to find a plane that's tangent. It's like built into this. But we're going to use that and the partial derivatives to figure out what's going on here and what the value is at a point very close to something that we know the actual value of. So f of AB, what's that? It's the value of the function at the point 1, 0, which is just
0.
which is just ln of 1, or in other words 0. So we want to figure out the function at at 0.9, comma, negative 0.2. So we know this is going to be 0 plus, now I'm going to take f with respect to x. So I'm going to just do that right here. So we have f with respect to x at the point 1, 0. So we're looking at this, and we have to take the x derivative of that. So this is the trickiest part of this problem. So who knows how to take the derivative of ln of x squared plus y squared? Yep. So it's u prime over u for where this in here is your u. So if you're taking the ln of something and you want to take the derivative of that, you do u prime, this right here, over u. And what that means is we take the derivative of whatever's inside of here, and we want to figure out with respect to x. So the derivative of what's inside of here would be 2x. So we have 2x over, because that's u prime, over u, which is just that stuff that's in there, which is x squared plus y squared. So this is my f of x. Does Does that make sense? Now I want to figure out what the value of it is at point 1, 0. So I plug in 1, 0, and I get 2 over 1. So my f of x is just equal to 2. Now I do the same thing with y, and my f of y is nice and easily just 2y over x squared plus y squared. And when I plug in 1, 0 for that, it's just 0. So I come over here, f of x times ab. F of x is 2, evaluated at ab, times x, which we know is that 0.9, minus a, which is 1, plus f of y, which is 0, times other stuff, so it would be 0. So, just evaluate, this is going to give us negative 0.1 times 2 is just negative 0.2.
It says it's at 100% because 6,000, but before it was at 7,000. This is the maximum capacity.
And that's your answer. Does that make sense?
Mm-hmm.
And now one thing I want to point out, just because it's cool and like the visualization is cool. You look at this and say, why is our f of y 0? Like, does it make sense for our f of y to be 0? So there's no change in our y direction where we are currently. So we look at where we are, and we're at this point 0. And if you move a very, very, very small distance directly up or directly down from that point 1, 0 right here, you're still at the same elevation. Because at this point right here, the line is vertical. If you zoom in really, really tiny. So if you move up or down, you're not changing the value at all, which is why the derivative with respect to y is 0. I just thought that was a cool thing to point out. Just kind of helping you see like the actual physical meaning of that.
Could you repeat that? Sorry, I couldn't see.
Oh yeah, sorry. So kind of just thinking why is f of y equal to 0? And we look over here at the picture, and we're dealing with the point 1, 0 right here. And f of y means how does the function change as you change y on a very small scale. So if you zoom in really tiny on that point 1, 0, our line is basically vertical. Because we have a circle, we have the right side of it, so the line's going to be vertical. So if we move a very tiny direction up or a very tiny direction down, our z value is still going to be 0 because we're following this curve. Which is why our function doesn't change as we move a little bit in the y, therefore our f of y is 0. And kind of seeing that visualization behind the math that you're doing, in math class doesn't really mean anything, but once you get into some of your higher level classes where you're using math to solve science problems, it can help you. It can help make the math easier, and it'll help you in the science aspect understanding what the math means. Like I said, I thought it was a cool thing to do. But with that, that's the end of this problem. Does it make sense? Do we get contour diagrams? Do we get tangent plane approximation? Because if we get both of those, that's 10 more points. That's 25% of your test is this problem. Again, assuming we have the same format. Really hoping they do. If not, they can't change it up that much. It's still the same concept. So we got these two down. And we're now done with, what was it? We had 6, 8, and 10. We have 24 out of 40 points of the test
I can leave now.
that everyone says we're good on. So we're looking at a good grade right now.
It's not out of 50.
I guess no.
It's not out of 50 points.
Like if we don't do anything else, we're at a 60%. And you know what? That's not bad. Yeah.
Is that a 40 or 50?
I mean,
What?
it's not bad, but
40?
it won't keep my scholarship.
D's get
40
degrees.
These get degrees, but not when.
So
Degrees
we're looking at a
like
60%.
But then
That's
you pay full
probably going to be,
tuition.
hopefully not, because
Not when
everyone's here.
degrees
It's
cost
probably going to be about
60,000
average.
a year.
You know, so like, that's only doing 3 questions. But we're going to do
I put
the
the D
last 2
in
questions.
degree.
We're going to get them right. Everyone's going to finish with 100.
Which one?
I didn't hear any no's, so we're good.
Which one?
Okay.
There's
So
one.
with that, what do we got next? We got some gradient and some directional derivatives.
Oh,
I'm
I
gonna erase
see.
all this.
Okay, no, tag team.
Tag team.
I'm command. I'm command V. You do the backspace.
Okay.
But we gotta wait. He's so unprepared. You never know.
No, it's fine. So that's why I have the underscore, so I can tell, like, because the reason I do this is so I can go back and label the times of each subject.
Okay. What are these things? They're like,
Oh, it's tape so that the projector stays down. Because otherwise it keeps on like moving.
so there's the cover.
Mm-hmm.
I thought it was like a sensor thing. I was like, oh, I wonder what it does. But I'm just dumb.
You're fine.
Wait, he wrote it. Wait.
Yeah, he wrote it, but is he starting yet? No.
I want to write it down, but like now I'm gonna be behind.
What? Yeah. Probably faintly, yeah. Right now, probably like 2.
Okay, so this one's got a couple different formulas in here that I'm going to write down first, and then I'll explain what each one is and what it means and how you can use it. Then we'll do a
There's
problem,
a space there. I don't like it.
and then we'll all learn things. So that's a symbol for gradient, and the way that what gradient of f means, the way that you find it is it's a vector that's just made up of f of x, f of y, f of z. So if you're given some surface, in order to find the gradient of that surface, f of x, f of y, f of z, boom. And what the gradient is the max rate of change. Vector for the surface. So the way that you can think about this, you're standing on a nice big circular hill, and it's like right in front of me, it goes straight up, right behind me goes straight down, and if I like walk in a perfect path along the side, I'm staying at the same height, right? So if I'm walking at the perfect path along the side, and I'm staying at the same height, and like balancing on the side, I'm walking along the level curve, because everywhere that I am, I'm at the same elevation. But if I'm standing here looking at this giant mountain in front of me, and I walk straight up the mountain, I'm walking in the direction of the maximum rate of change, right? The maximum rate of, if I want to get as high as possible, as quickly as possible, I'm going to walk straight up. I'm not going to, if there's any skiers out here, this works downhill too. If you want to go really, really fast, the maximum rate of change, you're going to point your skis both straight down the mountain, go really, really fast, and hope that you can stop in time before you hit the tree. I normally don't. But if you're a good skier and you're on a really steep black diamond, double black diamond, you're going to go side by side because you're not at the maximum rate of change. You're going down the hill more slowly. And if you were to go perfectly sideways, you would kind of eventually slow down and stop because you're not going downhill. There's no momentum getting added to you for going downhill. You're going on along a level curve. Did that make sense to anybody?
Mm-hmm.
No.
Sweet.
Not me.
There we go. So the gradient is both the magnitude and the direction of that straight downhill. And a lot of times it might ask you to it might ask for the direction of the maximum rate of change or the magnitude of the maximum rate of change. So you're going to find this and you're going to subtract one of the two out because this represents direction and magnitude. But if it's asking for just the magnitude, and this is the way that you find the magnitude of any vector. Yeah.
It's the rate of change out of point.
Yes. Yeah. It's the maximum rate of change evaluated at a point because you have to plug in values for your f of x, f of y, f of z once you get them. So the way that you find the magnitude of any vector, in particular the gradient vector, is basically Pythagorean theorem. You just do the square root of whatever your f of x is squared plus f of y squared plus f of z squared. So you evaluate your f of x, f of y, f of z at a certain point. You get a number, square each of them, add it, take the square root. That is your magnitude. So what that means is when I'm skiing down the mountain, I don't care which direction I'm going. I just care that when I'm going downhill, how fast am I going downhill? How quickly am I going down the mountain? I don't care which way you're going. I just want to know how quickly you're going. Now, the other side of that is the direction. The way that you find your direction, this is the magnitude of f. The magnitude of a vector is normally represented by the absolute value signs. So the magnitude of some function f is that. And if you want to find the direction of f, so, or in other words, the unit vector, because a unit vector has a magnitude of 1, so if you multiply anything by it, it doesn't change the magnitude, but it has the direction of whichever way you're trying to go. So the direction, the unit vector, is also a vector. So this is a number. This is a vector. And you do f of x over the magnitude of f, f of y over the magnitude of f, f of z over the magnitude of f. So whereas this one is, I don't care which way you're going, I just want to know how fast you're going. This one is, I don't care how fast you're going, I just want to know which way you're going. And again, these work with any vectors. We're just right now applying them to the specific gradient vector. But if you're given any vector in your mechanics class, in do you ever use this in E&M? Sure. If you're given a vector in E&M and you need to find the direction of it, that's how you do it. You take partial derivatives with respect to x, y, and z, put it over the magnitude, that's how you find the direction. And then the last thing that we can have is directional derivative. So directional derivative is saying, I'm now telling you, you have to go this specific direction. How quickly are you going down? So it might not necessarily be straight down. It might not necessarily be straight to the side. I'm now saying you have to go right here. How quickly are you going down? And what's the vector that results from that? So the way that you figure that out, so this is the rate of change in a certain direction. And the way that you figure that out is you take a gradient vector, which is your maximum rate of change, your maximum possible rate of change, and you do a dot product with your unit vector. And this will give you the rate of change in a certain direction. Yeah.
So for this type of question, they would have to give us the second vector, right? Or something to make a second vector.
Yeah, they would say, what is the rate of change in this direction? And like, I have an example that'll like show how they might ask it to you, but they'll give you some sort of, in this direction, what is the rate of change? You can't come up with it yourself. And I know we all know how to do, all know how to do dot products, right? Because we're all professionals at it, right? We did that MA123, we aced that class, we're all good to go. Everyone in here had to have passed it, at least. So otherwise we wouldn't be here. So we all know how to do it to some extent.
I did not pass the last gate. That's fine.
Okay. So with those three things on the board, we're going to go on to question 2 on my test. try and
He
fit
was
some
so
of it here.
stressful.
And what question 2 said was,
Yeah.
let we have f of x, y, z be equal to x, z, e to the y. Part A said, what is the max rate of change at the point P 2, 0, 1. And then it said, what's the direction? As a unit vector. So it says that's my function right there, x, z, e to the y. Find, I don't know why I did that first. Find the max rate of change at 2, 0, 1, and then find the direction as a unit vector. So we know our formulas because they're still up on the board. I want to find what the maximum rate of change is. How do I find that? Here. I'm going to find the gradient. So I'm going to take this, and the first thing that I got to do is find my f of x, my f of y, my f of z. So again, I'm going to do that right here to save some space on the main board. So my f of x, using this formula right here, a little box around it.
He's doing stuff over here. You should have.
Derivative with respect to x is just going to be z e to the y. And when I plug in my values of 2, 0, 1, I'm going to have 1 times e to the 0, which is just 1. Then I have f of y is going to be x, z, e to the y, because the derivative of e to the something is just e to the something. And this is going to be 2 times 1 times e to the 0, which all comes out to be 2. And f of z is going to be x e to the y, which again turns out to be 2, because it's 2 times 1. So now I have those three values, which means my gradient vector is just f of x, f of y, f of z. So my gradient is equal to 1, 2, 2.
Jake, would you write it with parentheses or like the vector notation?
I wrote it with parentheses. It's more correct to write it with the vector, like triangle things. But they didn't take off points for me writing with parentheses. But it's more correct to write it with those like triangle things because that means vector. So our gradient vector is 1, 2, 2. What do we do next? Because we still haven't found what they're asking us to find. What was that? Find the magnitude, because it wants to know what is the maximum rate of change. So we're going to find the magnitude of this. And all that we're going to do is we want to find the magnitude of f. So we're going to do f of x squared. 1 squared plus 2 squared plus 2 squared. 2 squared is 4. Plus 4 is 8. Plus 1 is 9. Take the square root of that. I get 3. Look how nicely they made that work out for you.
Okay.
So, the answer to this first part, what is the maximum rate of change, is 3. Because it's our magnitude of our gradient vector. Then it wants you to figure out the direction of your maximum rate of change. So then, we're looking at this right here. So, we already know what f of x is, we know what f of y is, we know what f of z is. And we know what the magnitude of f is. Pretty nice. So let's just plug stuff in. So we want to find the direction of the max rate of change. It's just going to be f of x, which is 1, over 3, comma 2 over 3, comma 2 over 3. and there's your unit vector for the direction of the maximum rate of change. Now, if you want to check yourself to make sure you did it correctly, the magnitude of your unit vector should always be 1. So you can then find the magnitude of this, and if it makes 1, then you're good. So here we'd square this, we'd have 1 9 plus 4 9s plus 4 9s equals 1. The square root of 1 is 1. So we know the magnitude of that is 1, so it is indeed a unit vector. So we're good. So the answer to this first part, maximum rate of change, is 3. The direction represented as a unit vector is 1/3, 2/3, 2/3. That all makes sense? Part B, I'm going to erase this. Part B asked us, find the rate of change of f at point 201 in the direction from P to Q. And it gave us a point Q. So it wants to find our rate of change from P, which we know is 201, to Q, which it gives us is 1, 2, 3. So find rate of change of f from 201 to 123. So now we're looking at a directional derivative because it wants to know a rate of change in a certain direction. So we need the gradient of f. Boom, we got that. Now we need a unit vector representing the direction that we're going. How are we going to find that? Yeah.
Find the vector from P to Q, and then divide each coordinate by the magnitude.
Yep. So the first thing that we have to do is we have to find the vector that goes from P to Q. And then find the magnitude of that, or find the unit vector of that, so we can plug it into that formula for directional derivative. So a vector from P to Q, we're just going to do, for each term, final minus initial for each coordinate. So I'm going to do 2, 0, 1, minus 1, 2, 3. That's false because we're going final minus initial. So we're going to have 1, 2, 3, minus 2, 0, 1. So we have our final position, which is Q, minus P, our initial position. If you did it the way I had originally written, you just get the negation of everything. They'd probably take off a point for that. So we're ending at coordinate 1. We're starting at coordinate 2. That means this, we're moving -1 in the x direction. We're ending at coordinate 2. We're starting at coordinate 0. That means we're moving +2 in the y direction. We're ending at 3. We're starting at 1 in the z. So we're moving 2 positive in the z direction. So this is your vector from P to Q. Now, all that we have to do is find the actual directional derivative of this, and I erased it because it was right here, but we're smart and we remember that all that we have to do is divide each of these terms by the magnitude in order to find our directional derivative. So the magnitude, I'm not even going to write this down because we're smart, we can do some mental math. We have to do this squared plus this squared plus this squared, take the square root of all of them. So -1 squared is +1, plus 4 is 9. Take the square root of that, our magnitude is 3 again. So our magnitude is 3. We say magnitude of PQ is equal to 3, which means our unit vector is just going to be equal to -1 over 3, comma 2 over 3, comma 2 over 3. Make sense how we got that? Then we're going to come right over here, and we know that we have to do our gradient times that direction, or dot product that direction. So we have our gradient, which is 1, 2, 2, dotted with negative 1/3, 2/3, 2/3. So we have 1 times negative 1/3 plus 4/3 plus 4/3, because we do that times that, plus that times that, plus that times that. Add all this together, and we get 7/3. And this is the rate of change. So we're on this hill. It tells us we have to go in this direction, negative 1/3, 2/3, 2/3. And that 7/3 is how fast I'm going down the hill, or in this case, up the hill because it's positive. So that is your rate of change in the direction from P to Q. Make sense? Any questions? No questions? That is 8 more points in your test, so this is another 20% of your test. Yeah. This? What? Because that one comes from our gradient of F. Whereas this one is negative because it's from P to Q, and that negative is represented in that negative 1/3. Cool? So you guys,
You'd be given the U vector, you would have to find that.
yeah, it's, well, you had to find this because it gave you that point.
Yeah, so you have to find that.
You have to, yeah.
But it gives you.
It gives you Q equals 1. It tells you that you have this point P2, 0, 1,
Did you do the master?
and it gives you Q as 1, 2, 3.
No, what did it today?
Well, you have to find what the vector is that gets you from
Yeah, I
P to
meant
Q,
like the master.
which is what we did in this step right here.
Oh.
Was we took our
Alright.
final point, which was Q,
Ah, this sucks
1,
with
2, 3,
quiz. I did that.
minus our initial point, 2, 0, 1. And we just did 1 minus 2, negative 1. 2 minus 0 is 2, 3 minus 1 is 2.
Yeah, no, I see that. I'm talking about the vector underneath it.
This
Yeah,
one?
Yeah, where's that?
This is the magnitude of that. Or, the direction of that. It's the unit vector. So we took this, and we divided each term by the magnitude to find the unit vector. Because the whole idea of that is, by multiplying something by the unit vector, you're not changing the value. So it's just like multiplying by something by 1 over 1 or by x squared over x squared. You're multiplying it by a magnitude of 1, so you're not changing the length of the vector, you're just changing the direction. Because we can't change how steep the hill is, but we can change which way we're facing. Is the way that you can relate that to the physical world. So does everyone else understand this? If so, we're now up to a 32 out of 40, which is a very respectable grade, because now we're at an 80%.
Okay.
And 80% I think most of us would be happy with. You shouldn't be happy, because you should be aiming for 100, so for nothing but the best.
Yeah.
But it's okay if you get an 80.
It's just okay.
Duck Life. Oh, yo, Duck
Just
Life.
okay.
Duck Life's lit.
Great.
Can you
Great
play this?
is a 90, and then like ecstatic is like 100.
It can like go in the water. You race it.
Not all these things, we just like to promote
of
people that are smart.
mechanical.
But like, this was, so this was the one test out of the 4
play
top
Duck
2
Life
tests
for
that I
free,
did get 100 on. I did poorly on some other, not relatively poorly on some other ones. But like, this was the one that I was really good at. So like, I like this stuff. But you don't have to get 100 on all of them to be teaching. Like I got some bad grades for me on some of these. These are some of my worst tests that I've taken.
Ooh.
And like I'm doing the reviews now, hopefully pretty well. So like, it's a tough class. If you don't get 100, don't feel bad just because I'm telling you 100.
Oh, is that like Spore?
But does this make
Never
sense?
played sport. I don't know.
Okay. So with that, we're gonna
So
move
no, I
on.
had the game Spore. On
Higher order
my
derivatives
phone.
and chain rule are 2 really quick things. And then that last local global extrema isn't really on the test, but there's a question that's probably going to be on the test that should fit in the category, but it's really a chain rule question. Weird, I'll just do the problem and I'll
Oh
explain
yeah,
it to you.
whenever
as we
it's
go.
chain rule, I don't do chain rule. I get
So
it
you're
right.
finding a maximum, but it's not really an external problem.
I do optimization instead of chain rule. It's so much easier. Oh shit! Change the title, boy.
Oh,
Or get ready. Yeah.
what is it?
I think we're doing chain rule.
Higher order derivatives, I assume.
Oh, this is so good to type on.
Yeah.
My keyboard is so obnoxiously loud, and whenever my roommate goes to bed early, all you hear is like. I'm like, oopsie.
Ripperoni.
Yeah, for her.
Mm-hmm.
For me, I'm fine. How do I? Oh. Oh. Okay.
Mm-hmm. Damn, girl.
How do I?
You can do Command A.
Oh, I just did that before too. I'm so dumb. And then, wait, you do the underscore. Oh, and then.
Dang.
Got him.
I can hire you. Except I don't get paid for this.
Clearly, I don't either.
Yeah.
Some of that YouTube ad revenue. You lost all your sponsors. Ad cuts.
I did. I had, I was a YouTube partner before they changed the requirements. So I couldn't have ads on my videos. I didn't have any ads on my videos, but like, I could have.
Mm-hmm.
That's what matters.
Yeah.
It's all the same. It's all the same thing. It's the same thing.
Oh. Oh shit, boy. What is that? What is going on?
That's so funny. Oh, let's do it.
Is it evolving?
Yeah.
Oh, so like the best one lives on.
Does it say 2x to the fourth?
Yes.
Okay. So higher order derivatives is just fxx, fxy, or fyy. The only thing that it really means is after you take the derivative with respect to x once, you're then taking the derivative of your new function with respect to x again. It's nothing more complicated. The only thing that could be helpful to know, although it hasn't come up recently, is what they actually mean. So just like if you have a parabola that's concave up, the second derivative is positive because if your second derivative is positive, you're concave up for that section. Your second derivative is negative, you're concave down. So concave up means it
Here
opens
comes that
up,
boy.
concave
Here comes
down
that
means it opens down for a parabola. So now expanding that to 3D, if we have f with respect to x with respect to x, so f double fxx, that just means it's and if that's positive, it's convex up. Right, concave up, yeah. Concave up in the x direction. So that means if you're looking at it, only the motion in the x direction, it would have a path like that. It would be concave up. Same thing with the y direction. And then what your fxy or your fyx tell you is how the x looks in the y direction. So how's your x changing as you move in the y direction? So it's not something that's, I wouldn't even think that this is going to be on your test, but if they start doing that multiple choice crap with you, that they're starting to like throw on your pop. Did you have multiple choice on the MA123 final? No.
No. You had to practice at it.
Yeah, because I heard like the first half of the semester, the 1 or 2 sections that was MA124, they had multiple choice on their, I think, final. I'm not sure about midterm. But like the math department started to throw in some weird freaking multiple choice, and like this could be something that they ask on a multiple choice. Like if your f(x(x) is positive, what does that tell you about the graph? And that
I
would
hope
mean
that's a
concave
question.
up
I'll
in the
get
x
that right.
direction.
That's like
Okay.
one question, right? 4 to 40. That's
So-
respectable.
Now, just to do quick little practice for taking higher order derivatives, we look at this to find our f of x, just do what we normally would do. So this would just be 8x cubed minus 15x squared y cubed. And then our fy would just be negative 15x cubed y squared minus 4y cubed. Again, that's just doing normal derivatives that we're used to doing. If I want to find f(x)(x), that means I look at fx and I take the x derivative of that. So the x derivative of this would be 24x squared minus 30xy cubed. And I want to find fyy. I take the y derivative of my f of y. So this is going to be minus 30x cubed y minus 12y squared. Now I get down here, fxy, that means I'm taking the y derivative of f of x. So I look to my f of x, and I'm going to take the derivative with respect to y. So that's going to go to 0. I'm just going to be left with negative 45 x squared y squared. My f with fyx, I do the same thing, but over here. And this is going to be negative 45 x squared y squared. And if you're smart and you see patterns, and you recognize that this is the same thing as this, that's good, because that should always happen. Your fxy and your fyx should always be the same. Yeah.
But then how come the graph is opposite? When you, like right there.
This?
Yeah.
Well, this is just what your fxy and your fyx is indicating how one variable changes in the direction of the other. So this is what this represents is this is how your x is changing as you're moving in the y direction.
I did.
Like how the
I was in a research class. I did a program.
so if you think of what just a normal second derivative
They
is,
like evolved robots. It was really
so we have our first derivative, which tells us.
They were like 3D robots. It's probably a video.
Where what research?
This is just,
I had a class in
Y
school.
is equal to
Like
X
I
squared.
worked with people who made the program.
and I know the first derivative of this is just telling me the slope along every given point, and the graph of that would just look like that.
This isn't mine, but like this is the program.
And then if I were to go one step further and say what's the second derivative,
Have you seen it?
or in other terms the
Out
slope
here.
of that, it would just be,
Mine was
Constant
in
y.
water.
Right.
So I have a bunch of.
so now we're doing
I
the
think I
same
have a
thing,
laptop
except right
with me
here,
that has,
now we're in
like, I
three
got a
dimensions, so it's a little bit more difficult to draw.
It was
But
lit.
we're looking at now
I can show
some
you. That
paraboloid,
was my research.
and we're taking the derivative. We now have z is equal to x squared plus y squared. So we have that. And if I take my f of x,
Ooh.
this is going to be what it looks like. My slope will be 2x. And the graph is just going to be a plane that slants up in the x direction. It's going to be level in the y direction. Does that make sense? Because my equation for this would just be 2x. So if I change my y value from 0 to 100, nothing changes in the graph. It only changes with respect to x. Does that make sense?
Yeah.
So when I take my f x, y, I'm saying how is this f of x changing? So like think of this as a new function. How is this changing in my y direction? And the slope of my x is not changing in my y direction. So this would turn out to just be a constant 0. Now, if I did the same thing the other way, here I would have 2y, and if I took the derivative of that with respect to x, I would again get 0. Does that make sense a little bit?
Yep.
Because it's representing how is the slope in my x direction changing as I move in the y direction, is what that second derivative means. If that confused people, it's not that important to understand, like I said, unless they throw in those multiple choice. It's going to be, this is how you take first derivative, second derivative, other second derivatives. If that makes sense, I'm going to move on. I'll just do like 20 seconds on the chain rule. We'll move into the last problem, and then we'll go for the night, and then ace the test on Thursday.
Okay. I suck ass at chain rule. I like whenever I have chain rule, I just like figure out a different way to do it. So I missed this lesson and
Yeah. Taylor polynomials.
Yeah, like second order differential equations, like using linearization.
Taylor polynomials ended.
No, they came back. They showed us an example where we had to make like, quadratic approximation. And it was on our workshop.
Yeah. Workshops will never be on tests.
Why do we?
Workshops are intentionally harder, so that way hopefully you can understand like a higher level of material. The workshops will always be harder than the tests.
Workshops are the worst thing.
Talk to your SGA representative. They're working on changing that.
Yes.
Change that.
Do we have SGA representative in the room?
Yeah, I actually just sent out like the proclamation that we signed that we're working on the like math recitations. And so out of 5, we gave them like a 2.2 review based on surveys and stuff. So yeah, we're actually kind of
You
working
should have
on
given
it.
them a 0.
We didn't do
Shit.
the reviews. You guys did. We just collected it, put it in the proclamation, signed it, and then sent it to whoever we needed to. So it's being worked on though.
There you go. If you don't like your workshops, you don't like your recitations, talk to my boy over here. Or another SGA representative so he doesn't get harassed by 5 Okay. So,
come on.
Harut
back to
deserves
chain rule
harassment.
right here that we got going on. So this is a different kind of chain rule, or the same idea, a different kind of chain rule than you're used to. It's just taking a derivative within a derivative, all that stuff. So the whole idea that we have is we have some function z that's in terms of x and y. But this x is dependent on t, so it's a function of another variable. And my y is also a function of that variable t. And I want to find how does z change with respect to t. So z doesn't change directly with respect to t. It changes with respect to x and y, which change with respect to x and t. So that's where our chain rule is going to come in. So what we can do is I'm going to say, I'm going to take a partial derivative of z with respect to x, but I want to get something with respect to t. So I'm going to multiply that by the derivative of x with respect to t. Because here you have a dx and dx. These will go away, and you have dz dt, which is what we want. But that's only a partial, because we still have another variable that we have to account for, that y. So we're going to do plus, and the same thing for y's. So you have the partial z with respect to y times the derivative of y with respect to t. Because again, these dy's will divide out, and you'll be left with dz dt, dz dt.
you say something on the derivative with respect to, does that mean that everything else is a constant?
Yes. Because this is another way of writing, although very awkwardly, like z sub x, where x is being treated as a constant or treated as a variable, everything else is a constant. So that's basically all the notes I have on the chain rule, because you'll see it in use more often. I remember that we had one work. Is that a question?
Yeah. For notation, does it matter at all when you write it like the D versus like the italicized type?
They shouldn't take off points for it. There is a mathematical difference between them. So I'll give like a quick 2 seconds. If you notice here, x is only dependent on t. So I can take the normal d, means you're taking the full derivative. So since it's only dependent on t, if I'm taking the derivative with respect to t, that's my whole derivative. Whereas when I come to the z, it's dependent on two different things. So if I'm taking the derivative of z with respect to x, it might also change in the y direction that I'm not accounting for here, but I'm only taking part of the derivative, which is why it's called a partial derivative, and you do the delta, the squiggly d. So that's the difference. If they take off points for you doing a squiggly d versus a straight d, go complain to your SGA senator. Or come to me and I'll complain to people. I'll yell at the professors for you. I've already passed the class. I can't do anything. But yeah, so that's the only difference between the delta and the d. But the last thing that we got, I'm just going to write down. So I'm going to write these down as rules for optimization, but they're not necessarily local and global external that you'll continue on to do, because that's what it kind of is. Just if they follow the same format that they have been following, this is going to be the 5th question on your test. So I want you to know how to do it. So if you have any type of optimization question, this is how you're going to approach it. So write some function, and like these steps will make more sense once I get into the problem. So write some function for what you're trying to optimize. Next one, take the derivative. Last step, plug in given conditions. So what I mean by that is, and this was question 5 on the test, how are we making out on time? Beautiful, and right on time.
Oh, okay.
This question, I'm not going to write down the whole thing. You can see how I write it out of the test, but it says, or when I send this out, you'll see how it's written. It says, a rectangular box has a square base of width W and a height H. So we have some rectangular box.
Did we do the same shit? Wasn't this the Guderius? Or not Guderius, it was on an SS page.
So it says a square base with width W,
this was a self-study, yeah.
and we have height H.
So I remember this was for chain rule, and I just did it.
Suppose that the width is increasing at a rate of 2 centimeters per second. So if the width is changing with respect to time, that's going to be dW dt. The width is changing with respect to time is 2 centimeters per second. If the volume of the box remains constant, which means my change in my volume with respect to time is 0, because it remains constant. What is the rate of change of the height? So it wants to know the rate of change of the height, so it wants dH dt. At the instant when W is equal to 12 centimeters and H is equal to 30 centimeters. And it says, hint, use chain rule. So, write some function for what you're trying to optimize. So, in this case, we know that we want to find dHdt based on this volume. So we're not necessarily trying to optimize the volume, but that's the overall condition that they're giving us. That's the restraint, that the volume has to stay constant. So what formula can we write that involves volume, width, and height that they give us? Yeah, so our volume would normally be length times width times height, but in this case, it's just width squared times height. So we have some formula for what we're trying to optimize. Now we're going to take the derivative. So what are we going to take the derivative with respect to? So we want to take the derivative with respect to time, so that way we can get dv dt, which we know something about. But there's a problem, because there's no time in here. But, says hint, use the chain rule, width is related to time, and height is related to time. So this is where our chain rule is going to come in. So we know that we're going to have, so we can't take the derivative with respect to time just yet. First, we're going to take it with respect to what we do have. So I'm going to take dv dw, and that's just going to be taking the derivative with respect to w, which is just going to be 2wh, and then dv dh is just going to be w squared. But now I know that I want the derivative of the volume with respect to time. So I'm going to have to do a chain rule, because volume is dependent on width and height are dependent on time. So I'm going to have writing it right up here. The derivative of volume with respect to time is going to equal, so right here you can think of your v is your z. So we're going to take dz dx, where we're going to say that our w's are x. So we're going to have dv dw times dw dt plus dv dh times dh dt. Yeah.
Yeah, that's what I was.
Solve it implicitly by doing
because
what?
let's say you have v equals w squared h, right? So
Yeah,
if you take, if you do
Just
product
drop it in terms of time.
2w dw dt h plus the other w squared dh dt, which is the same thing.
That is what this is.
Okay, so
So you could do that too. This is just, I like this because it's a more structured way of doing it.
Mm-hmm.
And like this is also the way that I learned it in high school. So this is a no want when problem. We know this, we want this, when that. But
Wait, what was he saying?
he's saying that you can derive it implicitly. So from right here, if we want to take dv dt from right away, we can say we're going to take the derivative of w, which would be 2wh, but then we want it with respect to t, so then it would be dw dt, which is going to be the same thing that you get over there. And then you would just do 2 plus w squared dh dt. Does that make sense? Yeah. So it's going to give us the same thing, because literally when we plug in right now, that's what we get. But like I said, I like to do it this way. But if you understand the implicit, that's perfectly fine.
Wait, if they say in the hint that we have to use chain rule, can't we just use?
I mean, this is the chain rule, just not. That is a good. It's not clearly shown. So like, I would write out this step first, so that way they can't argue that you're not putting chain rule down. But either way, we can now just plug stuff in here because we know that dv dt is equal to 0. We know that dv dw is 2wh. 2 times w is 24 times h is 1440. It's 720.
Let's do that.
Well, that's I'm not plugging in the 2 yet. But yeah. So this dv dw is 720 times dw dt. dv dh is just w squared, so it's 144 times dh dt, which is what we're looking for. You do a little bit of algebra, you get negative 1440 is equal to 144 dh dt, and you get dh dt is equal to negative 10 centimeters per second. And you get that right. That's another 8 points on your test. And we are now at a 40 out of 40. And we all got 100. Are there any questions?
Let's go back to reality.
Oof, there goes gravity.
Or like the higher derivatives and the chain rule, they're gonna ask like, just find a chain rule. Just find a higher order derivative like fxx.
It might. But like if anything, it's probably going to be incorporated into another problem. It's just like a smaller topic.
Oh, by the way.
That's okay.
If you have any questions, send me an email.
What was
if
the
you didn't
first
swipe
one?
in, you can swipe
I was
in.
watching it on here and I was like, oh shit, I don't know how to do that. I should probably come.
I don't remember.
Okay, I'll walk.
Oh.
Is that gonna stay on your page?
Good luck.
Oh, we should sign in.
See ya. I signed in, but I don't know if my